So let's show you how to do a moment of inertia by integration and also using the parallax theorem. So here is a uniform rod of length L. It is being spun at a distance of L over 6 to the right from the left end of the rod as indicated in the diagram here. And it says here in the statement that the length is L, the mass of the rod is M, and it is uniformly dense. And then the density for a linear rod, which is a one-dimensional analysis, is lambda, and that is the mass of the rod divided by the entire length of the rod. Okay, so let's do part A. We can start with the fundamental function to find moment of inertia, and that's by integrating r squared dm. But there's a couple of tricks if you pay attention. Hopefully you can see why we need to get rid of this dm. Okay, so the first association is that you have to recognize the density of the whole entire rod is mass over length by definition. And then you also need to recognize that if we integrate, we can just integrate a piece of the rod, which is a segment of the rod, and the density of the segment of the entire rod must have the same density as the whole entire rod because it does come from the same rod. Okay, since this is linear density, the density throughout the whole entire rod must be the same. So if you take a chunk out of it, that chunk must have the same density from where it came from, which is the density of the rod. So here we have lambda of the segment is equal to a piece of mass, and this again is changing to dm because we do need it in terms of calculus notation, and then a piece of the length, which is now instead of delta x, which is changed to dx. Okay. We can set these two functions equal, the density of the whole must equal to the density of the segment. So this little trick here is important because it kind of dictates the rest of the work. So we can set dm over dx equal to the density of the whole rod, which is capital M over the whole entire length, which is here. And then from here, we need to isolate for dm because in the original function, we have dm, but we cannot integrate with respect to dm. So we have to somehow substitute that out, and this allows us to do so. So solving for dm, you get this function here, multiplying both sides by dx. So that looks like this mass of the length, again, mass of the rod over the length of the rod dx. And that will allow us to substitute in for this dm up here. So in my work, you'll see that I carry the function down, but instead of r squared, we'll just change to r to an x now, since we're integrating with respect to the horizontal axis here. It's not a big deal. You can keep it as r if you want, but typically we change to x so that it's consistent with the dx here. Okay, but instead of dm, again, dm is equal to mass over L dx. So as you can see here, and here's the r squared term. We change r squared to x squared, and then instead of dm, we replace that with the density of the whole entire rod, and we can integrate with respect to dx. So that is a proper substitution there. Okay, and then if you notice here, the animation just comes up to show you where the substitution comes in from. And then in this particular next line, in the integral of x squared yields x cubed to the third, and then we pull out m and l because those are just constant. So when you integrate, you can just pull out m and l. Those are constants. And again, in case your calculus sucks, the integral of x squared is just x cubed over 3. Okay, and then what's more important though, because if you don't pay attention to this step, you can get lost in the algebra signs. The upper bound is L over 5L over 6 because this is your 0 where my cursor is, the axis of rotation, and then from the axis of rotation, the length of this particular segment of the rod is 5L over 6, and that's to the right. So that quantity is positive. However, your lower bound, while the diagram indicates that it's L over 6, if you measure relative to the axis of rotation where my cursor is, that cursor is going to go left, which means it's negative L over 6. And that negative sign is crucial to you not spending time doing a lot of backtracking with your algebra work. So in my work here, you see the cursor or the circle come up there, and that's L over 6. And the lower bound for this diagram is negative L over 6. And then from there, we just substitute in the upper bound into x cubed here. And then we also do the same for the lower bound, which is here. I use parentheses to kind of show you that it's important to use parentheses because that cube, that 3 there must be distributed to both the numerator and the denominator. So make sure you use parentheses, okay? And then the lower bound, again, I use parentheses here, and I keep that negative because the lower bound is a negative quantity, not a positive quantity. And then that negative sign in the function there, that's just come from integrating something where you take the upper bound and you subtract the lower bound. So that negative is part of the function. That negative is from the diagram itself because you got to go from axis of rotation to the left end of the stick. And if you distribute the power properly, 5 to the third power is 125. And then again, that L also gets cubed. So that's L cubed on the cursor there. And then 6 to the third power is 216. And then on the lower bound here, that is a negative sign. And we're cubing, so that negative sign stays there. And then it'll be L over 3. And then again, 6 cubed, which is be 216, which is in the numerator here. And then the denominator hasn't changed. That's just a common denominator of 3. And I just kept it over here just as that. Okay. But what you'll notice here, though, okay, is that this negative sign where my cursor is, and there's another negative sign here from the lower bound being negative because you had to go leftward. And that negative sign is going to cancel out, making it a positive sign. So here we have 125L to the third power. We're going to end up adding one more L to the third power, which is going to give us down here 126L to the third power. And both terms here in the previous line sits over a common denominator of 216. So I just combine that and put that in the denominator there. And don't forget about the common denominator 3 here on the bottom as well. So here you just got fractions to deal with. So from here, you notice we have a fraction divided by a coefficient of 3. So if you do your math properly, that you can just move the 216 in the denominator down here, down to the next denominator. So that would just be 126L cubed, and it'll be 216 times 3. And we simplify the denominator. That'll give us a product of 648. And the numerator hasn't changed. That's just 126L cubed. And I just carry that over. And if you reduce 126 and 648 properly by dividing by a common factor, you'll get 7 over 36. And then notice here there's an L in the denominator, and this is L cubed. So now that we're multiplying the L in the denominator, it's going to cancel out with one of the L's, giving us the final product of just L to the second power. So there is the moment of inertia for this rod pivoted at this particular distance away from the left end of the rod, which is L over 6. Okay. All right, so that's it for part A. And then part B asks us to use the parallax theorem. So I'm just going to clean the screen up a little bit here, and then let's knock out the parallax theorem. So for the parallax theorem, it is I nu, which is ICM plus MD squared. This D here is the distance shifted from the center of mass. So if you don't know the center of mass for a rod, you're kind of screwed here. You can just look it up. But the moment of inertia for the center of mass for a rod is 1/12 ml squared. So here, the orange line indicates where the center of mass would typically be. And then the distance there in purple that just came up, that's half of the rod. So that's indicated by using L over 2. And then it's important to understand what this D is. Sometimes folks get lost in what this D is and how to measure this D properly. D is the distance shifted from the center of mass. Center of mass in this diagram being the orange dashed line. And if you watch my cursor there, center of mass, and now the axis of rotation is shifted to the left, that distance. I don't know what that distance is, but I can find it. Okay, so don't just plug in L over 6. Kids who don't look at diagram carefully, you just plug in L over 6. But by definition, D is the distance shifted from the center of mass, axis of rotation, to where the new axis of rotation is, which is where this cursor is right here, based on the diagram. So we can find that distance real quick, just using basic elementary math. So D is going to be the whole entire half, which is L over 2. And that's where that L over 2 represents. And then we subtract it from this distance that's given to us, which is L over 6. And then if you do that, that is the distance shifted from the axis of rotation from center of mass. Okay. So we just carry this down. Again, ICM, hopefully you should know by now, it is 1/12 ml squared plus, and there's the m in that function, parentheses. So instead of D, D is equal to the whole left side, the half of the left side, subtract from that little segment that's given in the diagram. And if you do that, that's where that parentheses represent. And don't forget to carry down the square. Again, D is being squared. Okay, so from here, same line, I carry this piece down, the 1/12 ml squared, And then if you notice here, here's the 2 in the denominator, here's the 6. So common denominator would be 6. So multiply top by 3, multiply the 2 by 3. That gives a common denominator of 6. So we can just simplify. 3L minus L is going to give us 2L on the top. And then the common denominator would just be 6. Okay. And then don't forget to distribute the square here. That square is going to make this into a 4. 2 squares is 4. And then L into L square. And then the denominator here is going to be 6 square, which is 36. So here you have it. 1 half m, 1/12 ml square plus 4. Again, 2 squares is 4. 6 square is 36. L square is L square. And from here you can see that 12 and 36 has a common denominator of 36. So I can just multiply 12 by 3, and then I can also multiply the numerator by 3, which gives me 3 over 36. And then the 4 over 36 just gets carried over to this next line. And if you add the numerator, 3 plus 4 is 7. And then the common denominator is just 36. So you see that it yields the same outcome, which is 7 over 36 ml squared. And that's it for that. So if they don't really care for which way you do it, hopefully you can just use the parallax theorem, assuming you know your ICM and how to interpret that D. Now, if they ask you to do by integration, you do have to know your calculus. All right. Other than that, don't be whacked and stay nerdy, folks.